This is a lesson on net electric force in a unit on electrostatics. Net electric force, you may already intuit, works the same way when adding vectors as other forces. So the net force is going to be F1 plus F2 plus F3, blah, 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 with a vector notation here. And notice that means that you would want to separate the X and Y components, add up all the X components, add up all the Y components, and then you could find the magnitude of the net force if you use Pythagorean theorem, and you could find an angle relative to the axis using trig. We have learned in prior lessons that the best way to think about electric force is that it's Q multiplied by the electric field, and in the special case of point charges, you can get this equation here. So I have a couple of examples over here in regard to strategy for calculating net electric force. We're going to do the same thing that we've done with other forces. The signs on the forces are going to arise because of a coordinate system we've assigned, and you can see that in this example here, and we can this one as well has a positive x. We've assigned a coordinate system. So regardless of the value of the charges in here, you need to think about the signs on those forces in the coordinate system. Always draw the direction by thinking about the signs of the charges. But once you get that vector drawn, positives and negatives will come from the coordinate system. And so I'm encouraging you to draw the free body diagram, and if you turn in work for me, I will require a picture of a free body diagram. Draw the force on the object of interest, receiving that force, not on the object exerting the force. So when I look at this picture up here, let's call this QA, QB, and QC, just because there's 1, 2, 3 down here. I don't want to confuse QA, QB, and QC. Well, I might think about the forces on QA from QB and QC. And so what I would do is I would draw QA over here by itself because this is a free body diagram, remember free. And when I think about this, there's going to be an attractive charge from B. Okay, so on the free body diagram of A, I'm going to draw a force on A from B. And also, there's a repulsive force from C on A, and it's going to be smaller in magnitude. Not only is this charge half as much as the -1, it's also farther away. So this force is going to be, I'll call this F on A from C. And so you can see in this free body diagram, I have a couple of different forces that I can add up now. This is a one-dimensional problem, which are typically easier, and you will see in a lot of algebra-based courses will keep it on one dimension. So you assign a coordinate system, we can add these up, and we can set it to mass times acceleration or whatever we want to do with that net force. In a 2D situation, and I pulled this from the University Physics Volume 2 text, I can see that the forces here are drawn, and you can see how they're labeled, and that's consistent with how I've labeled up here. This force here is the force on 2 from 3. So when I look at charge 2 here, charge 3 is over here, and it's repelling it in this direction. So I would say that charge 2 and charge 3 have the same sign because they're repulsive. When I look at charge 1, its force on charge 2 is straight upward, force on 2 from 1. And so I'm going to say that charge 1 has an opposite sign of charge 2 because it's attracting. So this could be a positive, and a negative. I don't know. They don't tell us in the picture, but I can presume that much. Now that I have these two forces in 2 dimensions, I would add them together, and I can find that angle using trig. You would do Pythagorean theorem, and you could use the tangent somehow and be able to find that angle. And so if these forces, for instance, if I put another charge over here and I wanted to know the forces on it, I would have a diagonal along here, and this force would be at an angle in the coordinate system, and I would need to decompose it into its components, and then I could add, and that's the situation I'm talking about here. Decompose into the x components, decompose in the y components, and then you can add them. And so I have an example that I will do that is 2D, but I wanted to start with just a simple example in 1D just to see how this works in 1D. Because adding forces, netting forces is difficult enough as it is, and then we have the new electric force stuff to implement as well. So let's look at this problem, zero net force. And this is a common problem in this curriculum with this material. It says two charges, QA and QB. I'm noticing that they're both positive and they're not equal in value, okay? Are placed a distance 6 centimeters apart. At what distance from QA is the net force on a test charge equal to 0? Okay, so I'm going to draw a diagram. If you try to do this without a diagram, I think you're just searching around in the dark. So let's really ground ourselves on what's going on here. What I'm going to do is have a positive sign here. And I'm going to call this the origin because it says at what distance from QA is the test charge equal to 0. So we're going to be measuring from A, and so I'll just call the origin where charge A is. And so there's the x-axis and there's a y-axis. We don't need it, but it just kind of helps me identify where the origin is. So this is QA. I'm going to draw QB over here. QB is also positive, and I can do it that way. And the way I taught when adding electric fields is the same way we're going to use for adding electric forces. I'm going to look at the vectors. And in this situation, they want me to figure out where it's 0. And I have 3 possible regions where it could be 0. It could be 0 in region 1, it could be 0 in region 2, or it could be 0 in region 3. I don't know yet. But I will look at the direction of the vectors and get a better idea. So what I will do is if I put a test charge in here, it just says, what is the net force on a positive test charge equal to 0? So if I put a positive test charge in here, I'll look at the forces. If I put a positive test charge in here, I'll look at the forces. And if I put a positive test charge in here, I'll look at the forces. So let's look at the force from QA. So this is going to be on the positive test charge from A. In the region 1, they're repulsive, so the force would be in this direction. In region 2, I can see that this positive charge is still repulsive, so it'd be in this direction now. And in region 3, the positive charge A will exert a repulsive force on the positive test charge. So that's the direction of the force on that positive test charge due to A only. Let's draw in B. So I will do this. The force on the positive test charge due to B. Well, let's see. B will exert a repulsive force on this test charge as well. So it'll be repulsive in this region, and also repulsive in this region, and also repulsive in this region. And so you can very quickly see how this vector diagram is giving us the tools to be able to determine where along that x-axis that the net force could be 0. It cannot be 0 in this region because they add together, and it cannot be 0 in this region because they add together. It has to be in between. So that helps me designate a variable that I'm solving for in the problem. I will be looking for this distance, which I will call RA. And I'm also going to note that the distance between these two charges, they tell me, is 6 centimeters. So that means RB is going to be 6 minus RA. So I'll be able to use that relationship when I set up my equation. So that positive test charge has a force in each direction. I can say F net equals MA. The net force is going to be the force on that positive test charge from A minus the force on the positive test charge from B, and it's going to add up to 0. And so very intuitively, we're going to get F on the positive test charge from A has to equal the magnitude of the force on the positive test charge from B. So let's plug in what we know. So now I can use the force equation for point charges. I'm going to know also that I have a charge A, and they use a big Q for A, right? Big QA and big QB. And then the charge on the positive test charge, I'm just going to call Q. And I don't even have a value for it. You'll see in a second why we're just using a positive test charge. So let me plug in what I know. The force on the positive test charge from A, I'm going to use the point charge equation here. I get the electric constant times QA times that positive test charge, whatever that value is, divided by RA squared. And that will equal KQB times that positive test charge over RB squared. Okay, so you see why I don't need to know that value of the positive test charge, because it cancels on both sides. And I'm also going to point out here that really what we're doing, because that positive test charge canceled, we're setting equal the electric field due to QA equal to the electric field due to QB. Again, F equals Q times the electric field. So if there's a zero force, that means that the electric field also has to be zero as well, the net, right? The net force and the net electric field has to equal zero. So the two electric fields have to be zero. I'm going to continue solving out here. So we get, and I'm going to get the charges on one side, the ratio of charges on one side, and then the radii on two opposite sides, and then I'll be able to take a square root. So let's do this. I'll do RB squared equals, and I'll multiply QB over QA times RA squared. Okay, and you can check my algebra on that if you like, but I'm pretty confident. I can put in what I know about RB, 6 minus RA, and that quantity is squared, equals QB over QA times RA squared. Again, the strategy here, the easiest thing to do, I know your instinct might be to expand this expression, but it's way easier just to take a square root on both sides here. And what you see is that you get 6 minus RA equals the square root of the ratio of those two charges, QB over QA times RA. I'm going to isolate RA on one side. RA will equal, this will come over here, so I'm going to get 6 by itself, and then I can factor an RA out, and I get 1 plus the square root of the ratio of those two charges. And again, you can check my algebra. So I'm going to plug in what I know, 1 plus the square root, and these are in microcoulombs, but I have a ratio here, so if I convert, it'll just cancel on top and bottom. So I'm just going to do a ratio of those values. So I want QB, which is 0.8, over QA, which is 0.5. And when you run that through your calculator, you get RA equals 2.649 centimeters. About 2.65 centimeters is what that is. And so I'm okay with that. It's smaller than 6. That's what I expected. Another thing I can look at here is that I do expect the electric field to be equal and the forces to be equal closer to RA because it is the smaller charge. In order for it to have this inverse relationship, in order to have a larger force, I have to get a smaller distance, and that will help that charge have a larger field or force compared to the larger force over on the other side. So that's how you would do a 1D force analysis with the point charges to find a net electric force